So in our previous module, we covered complex numbers, and now we shift a bit. So we are done with the basic real and complex number system and their properties and arithmetic operations involving real numbers and complex numbers. So, but we also had module 4, which was on functions. So polynomial functions and their properties, and also trigonometric functions and their properties. So we'll now shift now to geometry, where we'll consider vector numbers and the vectors and their representations in matrix form. And then later on in module 7, you'll have lines and areas of geometric figures, conic sections, and yeah, so basically module 6, 7, and 8 to be on geometry. Then we shall have module 9, which takes us back to the counting principle, that is in module 9 and module 10. So module 6. So let me just use the notes for a quick review. These are not new concepts to us, so it's just a quick review so that it can help you go through the learning activities given. So in this module, we'll just look at vectors and their properties. Ideally, vectors and matrices gives us a way of representing real numbers depending on the definition given. So we shall look at vectors and their operations. We look at matrices. We look at arithmetic operations on matrices and how you can use properties of matrices to calculate areas of geometric figures and volumes of objects using determinants. So when you go back, so we had a real number system and then the complex number system. So in some cases, you'd require to look at an array of numbers, and this is where now vectors come in. So you're looking at a set of numbers that are related by a certain property. And if it's possible to write those numbers as an array, then you can carry out arithmetic operations on the numbers by defining them either as vectors or matrices. So we shall start first of all with vectors, and we look back at the Cartesian product, where in our module 2, we define the Cartesian product as the set of ordered pairs of elements in two sets A and B. And out of the Cartesian product, we had the geometrical representation of the Cartesian product on the Cartesian plane. So we have the two sets A and B, and you're ordering elements in A and elements in B. So the resulting ordered pair is XY, and we can represent the ordered pair on the Cartesian plane. So the element P here would be the ordered pair X, XY. So after that, we have the two sets. So if you consider the point of intersection being the common element, so this would be the common element. So an element in A and also in B. So if you consider the point of intersection, and then you have a line segment emanating from the point. So we have the origin in this case, which is the point of intersection. Consider a line segment emanating from the point to our ordered pair P. Then the resulting line segment is what we refer to as a vector, and it's directional. So we are emanating from a point. But it doesn't have to be from the origin. So this is just the basic representation of a vector. You could also have a case where you have 2 points on the Cartesian plane. Then you join the points then the resulting line segment is also a vector. So it doesn't have to emanate from the origin. So a vector is directional. Directional meaning that it has the initial point and it also has the terminal point. So, and depending now on the direction, then we can have we can represent, depending on the direction of the vector, it can either be represented by a negative sign or a positive sign. So we shall explain when you have the negative and the positive, but ideally it will have a positive sign if the direction is from the initial point to the terminal point. But now if you change the direction whereby you're moving in the opposite direction, then it will have a negative sign. But the negative here is not for magnitude. So the magnitude of the vector remains the same. But the sign tells us the direction of the vector. Is it in the reverse or is it in the from the initial point to the terminal point? So as you go through the module, you'll find the warm-up quiz, and then you have supplementary reading where you can read more on vectors and matrices, so that will come in later, and some videos which you can watch to just help you understand more on vectors and their properties. But to give a quick review of the module, I want to use the module notes, and so that we can quickly go through the content, and if there are any questions, then you can respond from there. So I've given the demonstration with the two-dimensional space, but you can generalize the representation of a vector to the Euclidean space, that is the n-dimensional space Rn. So in my demonstration, I use the intersection of two sets. So the Cartesian plane is an intersection of two real number lines. So in this case, then the Cartesian products will be R cross R, represented by R to power 2. But you can also generalize to Rn. So it doesn't have to be two ordered pairs all the time. So you can still have the Euclidean space, which is still a Cartesian product, which is still a representation of ordering of real numbers. But in this case, they will not be pairs. It will be an n tuple. So you are listing n elements. So for R2, you list two elements, A2 ordered pairs, but you can still order n real numbers, A1, A2 to AN. So you have an n tuple as a representation, so that for ease of understanding, you consider the two-dimensional, but you can generalize now to the n-dimensional space, whereby the vector now is the n tuple, an ordering of n elements. But for the Cartesian plane, you're ordering two elements. So, and just like in the case of real numbers, we can carry out various operations on vectors. Say, for example, if you have a vector in R2, say you have two vectors V1 in R2, and say the vector V1 is the ordered pair A1, A2, and the vector V2 is the ordered pair B1, B2, then just like in the case of real numbers, you can add vectors, you can multiply vectors by a scalar, you can subtract vectors, but later on you're going to look at the product because it's different. So far we'll look at vector addition and scalar multiplication, whereby you're multiplying a vector by a scalar. So sorry, so we can still define operations, but for now, we only define the two operations, vector addition and scalar multiplication. So whereby if you have these two vectors given v1 and v2, and you want to find the sum v1 plus v2, then you consider the elements in the vector and you add corresponding elements that occupy the same position. So the resulting vector here would be a1 plus b1, comma, a2 plus b2. And please note the brackets I'm using. Open brackets for vectors. Remember, for sets we were using curly brackets. Reason why you need to be careful when you write a set. So, but for vectors we use the open brackets. I'll explain later why you cannot write a vector in this form, because it means something else. So always represent vectors with an open bracket. So when you add vectors, you add corresponding elements. For example, say I take the vector v1 to be 1, 2, and the vector v2 to be, say, negative 2, 4. So then I can add v1 plus v2, add corresponding elements. So 1 plus negative 2, comma, 2 plus 4. So you add corresponding elements. How about scalar multiplication? Scalar multiplication is simply whereby you have a vector, say v1, say a1, a2 to an, and you want to multiply the vector by a scalar, say kv1, where k is a scalar. So because the scalar could either be complex or real, then you represent the field of scalars by capital K. So you can find kv1. So kv1 here will be ka1, ka2. You multiply every element in the vector by the scalar. So a good example would be, say you have v to be the vector 1, 4, 5, and you want to find 5 multiplied by v. So multiply every element in the scalar, in the vector by the scalar. So you have 5, 20, and 25. So we start off our set of vectors with these two main operations: vector addition and scalar multiplication. And for these two operations on vectors, we have the general properties that when you're working with vectors on the real space, when we talk about the real space, we simply mean that the entries in the vector are real numbers. So we'll first of all start with real, then later on we'll generalize to complex numbers. So for vector addition and scalar multiplication, we have the following properties. So the first property is that when you're adding vectors, the direction doesn't matter. So you can either, if you're adding two vectors, so they are commutative, they actually commute under addition. That when you add, whether you start with u or start with v, then the result will still be the same. Then you have the associative property. So the associative property allows you to distribute the brackets. Again, if you're adding more than two vectors, you can start with any two, and then once you complete the operation in the parentheses, then you can work with the third element. Then you have the existence of the additive inverse. So this depends on the space, that we always have what we call the zero vector in a space. For example, if I have R2, the zero vector here would be the vector 0, 0. If I'm in R3, the zero vector will be the vector 0, 0, 0, and so on. So then in general for Rn, you have the n tuple, an ordering of n zeros. And you notice that if, for example, I take the vector, say v, to be the vector 1, negative 4, 6, and I take the zero vector in L3, so my zero vector in L3 is v0, 0, 0. And then I find v plus v0. You notice that v plus v0 would be 1 plus 0, negative 4 plus 0, 6 plus 0, which is 1, negative 4, and 6. So the vector remains unchanged. Reason why? we call it the additive identity. It leaves the vector unchanged whenever if you add the two vectors. And then the other property now on R is the existence of the additive inverse for a vector. So for any vector V, you'll always find an additive inverse in the sense that when you add the two vectors, the resulting vector is a zero vector in the space. For example, my vector here V1, 1, -4, -6. If I find negative V1 is the same as -1 multiplied by V1, and we said that when you multiply a vector by a scalar, then you multiply every component in the vector by the scalar. So we have -1, 4, -6. So what do you get when you add V1 plus negative V1? So kindly indicate the answer in the chat. So add the two vectors V1 multiplied by negative V1, and please note the operation we carried out here. We want to find negative of V1. So first of all, consider negative to be the scalar, -1 multiplied by V1. And when you multiply a vector by a scalar, you multiply every component in the vector by the scalar. So I want you to add V1 plus negative V1. Yeah, thank you, Nicodemus. So you notice that it gives you the zero vector. So that the resulting vector now, -1, negative V1 is what we refer to as the additive inverse. So then you have distributivity over addition and also over scalar multiplication. But you all recall BODMAS, so you have to be careful. You cannot distribute addition over multiplication. So, but you can distribute now multiplication over addition. What I mean by you cannot distribute addition over multiplication, if for example I have A plus V multiplied by U, then this will not be the same as A plus V multiplied by A. You see, this is wrong by BODMAS. So you can only now distribute multiplication over addition. First of all, you finish with the operation in the parentheses, then you distribute. So we have the distributivity property, and there are two here. So we have the right and the left distributivity property. Then we have this should be ideally be not be distributive. This is an error. This is associativity under multiplication, that you can start by multiplying any two and then you multiply with the resulting element. Then again, under vector operations, you have the multiplicative identity. We always have the 1. So, and this 1, in this case, it's a number because you're in the real space. But in some cases, it could represent even what we refer to as the identity in the space, the multiplicative identity. So the number 1 is just a representation. So it can be 1 depending on the vector space you're defining. It could even be a matrix or another function that serves as a multiplicative identity. But simply means that once you multiply, then it remains unchanged. So we have the graphical representation of the operations that I had discussed earlier on. You can add two vectors, u plus v. You have the resulting vector, and then you have the resulting vector u minus v. So you notice that here, if you have your vector u, so it's directional. This the reason why these arrows are important. So if I'm to move now from the terminal point to the initial point, then the resulting vector here would be negative v. If I'm to move from the terminal point to the initial point, then the resulting vector here would be negative v. And it is directional, so you have to be careful when you're considering vectors. So for example, look at this vector. The vector u minus, the resulting vector in red. The resulting vector in red, the terminal point is here and the end point is is here. So if I'm to compute this vector using my vectors given here, it means I'll have to move from in this direction, then go in this direction. And in the opposite direction, then the measure here is negative v. Then this retains the direction you have, uv. So that the resulting vector represented here is negative v plus u. Reason why we have u minus v. So look at this one. So you have the terminal point is here and the end point is here. So you're starting from this point and then you have an initial point here and a terminal point there. And these two vectors are the same since they are parallel. So the measure of the vector here is v. So you have u plus v. That would be the resulting vector. So from the initial point to the terminal points. Then yeah, so scalar multiplication, I've demonstrated scalar multiplication. You multiply every element in the vector by the scalar. I gave an example on vector addition and multiplication that was covered. And then we have the magnitude of a vector. So the magnitude of a vector follows from Pythagoras theorem. So if, for example, I take R2, it's normally easier to represent by R2, and then you can generalize to the entire space. So you can generalize to the entire space. So this is R2. And then you have these two, you have this vector on R2, say the vector, this is x1. Let me use the A's. So you have A1, you have A2. Okay. Okay. So that's a vector, the resulting vector. So if I want to find the magnitude of this vector, then it's A1. So the measure here is A1 units and the measure is A2 units. And so by Pythagoras theorem, the magnitude of the line segments OP would be the square root of A1 squared plus A2 squared. And then you can now generalize. You can now generalize to Rn, an n tuple. We look at R2 because it's easier to visualize, but you can generalize to Rn. Yeah, so you can find, and you can even calculate the measure, the magnitude of the resulting vector after carrying out the arithmetic operations. So for example, the magnitude of v plus w, negative v plus 2w. So now, before now I look at, yeah, so then you have the column vectors. So what we have these two representation of a vector, a1, a2 to an. So this is the standard representation of a vector and we call it a row vector. And then if you are to represent the same vector in column form, then we use the following representation. Reason why you have to be very careful with the brackets. So you notice now the brackets have changed since you have your vector in column form and you have your vector in row form. So is there any questions so far up to that point? Because I now want to move on to matrices. Any question? Someone, please proceed.
I didn't understand how, I don't know who typed the answer on the chat box, how they arrived at that. Maybe I got lost in between.
Okay, so yeah, so yeah, it's okay. Thank you for asking. But next time, if you have a question, please feel free to interrupt me so that I can respond at that point, because it means then we might have left you at that point. So if you have a question, you feel free to interrupt and ask a question. But the question I think was on inverses. So if you have a vector v1, 1, 0, let me not use 0. I can even use 1, 2, -7, and 8. And find the vector negative v1. So can we find the vector negative v1? So you can type the answer in the chat, please. All of us, we can type the answer in the chat. So find the vector negative v1. I'll take the first one that comes on the chat. It kindly type the answer in the chat. The vector is 1, 2, -7, 8. So what would be the vector negative v1? The vector negative v1, so -1, -2, 7, -8, correct. So the vector negative v1 is -1 multiplied by v1. This is a very important step. So you're multiplying v1 by the scalar -1. So multiply every element in the vector by -1. So you have -1, -2, 7, -8. Then now we add v1 plus negative v1. So we have 1, 2, -7, 8 plus -1, -2, 7, -8. Sorry, -8. So we add the two, so add corresponding components. So 1 plus -1, 0, 2 plus -1, -2, 0, -7 plus 7, 0, and 8 plus -8 is 0. So that is how we arrived at 0. So when you multiply vectors by a scalar, you multiply every component in the vector by the scalar. And when you add vectors, you add corresponding components. I hope it's clear now. Is it clear now?
Yes.
Okay, good. Any other question before I move to matrices? Basically, that's it. Those are the basics of vector addition. But note, please note this, because I know we have linear algebra in year 2. We have started with two basic operations: vector addition, and scalar multiplication. Multiplying a vector by a scale. I have not defined products of vectors. I have not defined products of vectors. So these will come in later. So far the basic operations are vector addition and scalar multiplication. Okay, we are going to introduce products later. So now we move on to matrices. Why do we need matrices? So first of all, we said that vectors, sorry, there's a question. So now vectors are meant, vectors represent an array of related elements. The moment we represent the vector OP, So the line segment OP is representing the relationship between the real number A1 and the real number A2. So we can have a vector represent ordered elements. Ordered means that there's a certain rule that is relating the two elements, the elements. So they can be ordered pairs, ordered triples, or ordered n tuples. But you could now also have a case where vectors are related. So you have the vector v1 and another vector v2, and you want to connect these two elements. So you can have an array representation of related vectors or ordered vectors. But I don't want to use ordered, but they're just you're just representing a connection between the two vectors. And I just want to give a random real life case of vectors. So for example, with the assumption that let's take a hardware shop, and in the hardware shop, we are selling copper rods. We are selling, which is the other type of metal, steel rods, and we are selling, say, aluminium metallic rods. So this is I mean, it's a hardware shop. And then, so when it comes now to copper rods, I want to look at to find the profits when I'm able to, to just represent the sales per week. So the sales per week. So a week has 6 working days, let's assume. So I want to represent the sales per week for the copper rods. So I can represent the sales per week on that week by a vector. So say maybe day 1 I sold A1 copper rods. Day 2 I sold A2 copper rods. Day 3 I sold A3 copper rods. A4 copper rods. A5 to A6. Then I can have my sales for the steel rods. So I have B1, B2, B3 to B6. And then I have my aluminium rods C1, C2 to C6. So I have my sales of the 3 products. But now I want to make my calculations now to connect all the sales. I just want to come up with a representation of the sales for that week. Then now this is where matrices come in, whereby I can either have an array of the vectors. Say, for example, the first row has the sales for the copper rods. The second row has the sales for the steel rods. And the third row has the sales from the aluminium rods. So first of all, you have a vector, and then you can have an array of vectors. So this is where now matrices come in. And in the case of real numbers, matrices now would be an array of real numbers. So you have an array of real numbers, and you have the either in rows, and it contains rows and columns. Like here, column 1 will represent the sales of day 1. Column 2 will represent the sales of day 2, and so on up to column 6. So matrices provides an easier way of data representation, and they play a vital role when it comes to data analysis, because if you're to define your model, then you need to have a representation of the data under consideration. And so it's important for us now as because mathematics is actually at the core of modeling or any computational methods. And so we must find a way of representing our data. And normally when it comes to data, you're studying Python, you know how it works. So first of all, you have to train the data you test, you have to first of all test your model on a sample. And then if it's working on a sample, then you can generalize. So the same case applies here. We'll start with smaller spaces, even R2, just ordering two elements. or R3 or R, and then generalize to Rn, where n can be a very big model. It can even n equal to 1,000, because if you can train the model on R2, then you can train it on Rn. So we'll understand the properties using a small dimensional space, say R2, R3, and then we can generalize, because any number is related to 3, 2, or 3, either odd or even. So if it's working on 2 and also working on 3, then it should also work on the entire space. But basically now matrices are used for data representation, and so we'll start by looking at properties of matrices. How do you add matrices? How do you multiply matrices? And then how do you find scalar representations of matrices? And then later on now in our linear algebra, we'll go deeper into properties of matrices and various operations involving matrices, and how we can now connect them to the various computer algebra systems and programming languages that will come later in year 2. So for now, we're just looking at basic properties, because you have to understand a tool before you use it. So we are kind of reading the manual now, how to carry out the operations using matrices, so that at the point where you're modeling, then you'll be able to understand what you're working with. So I mentioned that a matrix is an array of numbers arranged in rows and vectors. And we have the following special matrices which will come later. The zero matrix. So this would be a matrix in which all the entries are zero. You have zeros everywhere. And then a matrix consists of rows and columns. So you can have a matrix of this form. In this case, our matrix has n columns and m rows. And we say that the matrix is of order m by order m by n. In cases where m is equal to n, same number of rows is equal to the number of columns, then the matrix is said to be a square matrix. And it's out of the square matrix that we have the identity matrix. So the identity matrix here would be the matrix in which the entries in the diagonal are equal to 1, while all the other entries are equal to 0. An example is the identity matrix in R2, denoted by I sub 2. So the identity matrix here would be not in R2, it cannot be in R2. So if you're in the space of 2 by 2 matrices. So if a matrix is a 2 by 2 matrix, will look like a 2 by 2 matrix would look like this. It has 2 rows and 2 columns. And then you have the identity matrix in this space would be the matrix 1, 0, 0, 1. A matrix in which the main diagonal entries are equal to 1 and all the other entries are equal to 0. So this is the main diagonal. And then you have the secondary diagonal, and then you have the other elements. So now, how do you add matrices? How do you multiply matrices? Because basically mathematics is about addition and multiplication. So anytime you introduce a new concept, then you have to consider the arithmetic operations on that set of vectors. So for example, now I have two matrices. So my matrix here is a matrix of order m by n. So how do you add matrices? So when you add matrices, you add corresponding components that occupy the same position in a matrix. Like I can write my matrix B here to be the matrix B1, B12, B1n, B21, B22, B2n, BM1, BM2, BM, Mn. So when you add matrices, then you add corresponding components that occupy the same position. And the subscripts here will guide you. So A11 means that it is the first element in row 1, column 1. The first element in row 1, column 2. First element in row 1, column n. First element in row 2, column n, and so on. So that when you're adding the elements, then you add corresponding components. In general, if you have your matrix Aij of order m by n and the matrix Bij of order m by n, then the resulting matrix A plus B should be Mn. Just adding corresponding elements. But note, since you're adding corresponding elements, then the matrices must be of the same order. So you can only add matrices of the same order. Otherwise, you'll have an element without a corresponding element. For example, look at the matrices given here. So we have, say, matrix A, B, C, and D. So if you look at these matrices, we cannot add them. Like I cannot find A plus B because they're not of the same order. This matrix is of order 2 by 3. It has 2 rows and 3 columns. This matrix is of order 3 by 2. It has 3 rows and 2 columns. This matrix is of order 3 by 3. And this matrix is of order 2 by 2. So if you are to add the matrices, they have to be of the same order, like in the example given here. Same number of rows, same number of columns. How about when you multiply a matrix by a scalar multiplication? Some of these things you can compute with a calculator and computer algebra systems. So I'm sure maybe you're wondering, why should I bother when I can just key in these values in Maxima and get an answer, or when I can just use a calculator and get an answer? So remember, those are programmed tools. And we are in a we are in an evolving digital space. And we are looking at innovators, people who are going to start doing things differently. But you must first of all understand the basis. What are the foundations, so that you can easily be able to identify the room for changes. So therefore, it's important that we understand the theoretical background. Then we can move on now to innovations and improving what is already existing. So for scalar multiplication, say you have a matrix A here and you want to find 2A. Then just like in the case of real vectors, you multiply every component in the matrix by the scalar. So you have 2 multiplied by 1, 2 multiplied by 3, 2 multiplied by -1, 2 multiplied by 4, 2 multiplied by -2, 2 multiplied by 5. So multiply every element in the matrix by the scalar. So that the resulting matrix here will be 2A would be the matrix 2, 6, -2, 8, -4, and 10. So that is vector matrix addition and scalar multiplication. But note, you can only add matrices of the same order, because when you add corresponding components. Again, for scalar multiplication, then you have to multiply every element in the matrix by the scalar. So more examples there for you to look at, and yeah, an exercise there. Now, matrix multiplication. So is there any questions so far on matrix addition and matrix multiplication? Any questions? Are there any questions? Give me a nod on the chat. If it's clear, then you give me a nod on the chat, then I can proceed kindly. I don't want to leave anyone behind. Is it clear? Okay, great. Thank you. Any question? Okay, so then, sorry, you have a question?
Yes, just to clarification.
Okay.
Does it matter
Mm-hmm.
the position of of a figure in matrix? If, for example, a set of matrix A,
Mm-hmm.
then okay, like whatever you're showing in the screen where you said
Yes.
let A be 311 and
Mm-hmm.
B 530.
Yes.
Uh, is it in order if for matrix A here we have uh, for the position where there's 3, we have a
Mm-hmm.
figure that is 2 numbers or in tens.
Mm.
Then the next one where there's 1 is a ones and the other
Oh,
one is a
yeah.
hundred.
Yeah,
Do
no.
you get me?
Yeah, thank you. Thank you for that question. It's only that for examples, use very simple examples. But whenever we write the matrix, the general representation of a matrix, the AIs here are real numbers. These are real numbers. These are real numbers. It can even be 1,000. It can any real number. So it doesn't have to be in ones. It's only that for ease and quick computations, you use ones. But you can have a matrix even that looks like 1,000, 2,000, 3,000,000, whatever. So as long as the entry is a real number. And later on, we shall have even complex matrices where the entries are negative I, 1 plus I, that is one entry, 2 minus I, 4 I. It's a matrix, but in this case now this is a complex matrix because the entries are real. So the entry here can be any real number. It's not limited to ones. It's only that in my examples I use one for ease of computation, but it can be any real number. It's not limited to the ones only.
Okay, thank you.
Okay, great. Thank you. Thank you for that question. So we just use simple examples to demonstrate, just to enhance your understanding. Now, let me look at matrix. Matrix multiplication is, remember, I did not introduce vector addition, vector multiplication. So we only looked at scalar multiplication. And so when you're multiplying matrices, say for example, you're multiplying the matrix 1, 0, 5, negative 1, 3, 2, 3, 1, negative 1, and you're multiplying by 2, 2, negative 1, 4, negative 1, 2, 0, 4, 0. And you're multiplying the two matrices A and B. So remember, the entries are representing vectors. So this is a vector, this is another vector, this is another vector, this is another vector, this is another vector. So what that means is that when you're multiplying matrices indirectly, you're multiplying vectors. So how do you multiply vectors? So we'll start by, first of all, demonstrating multiplication of uh, multiplication of a row vector. A row vector in this case would be a vector that has one row. So this is a vector that has one row. And sorry for the confusion. Yeah, it's okay. It's a row matrix, actually, not a row vector. It's a row matrix. So this is a row matrix, a matrix that has one row and p columns. Then we have the column matrix. Column matrix B11, B21, B11, B21. So this is a row matrix and this is a column matrix. So a row matrix has one row and p columns. So the order of the matrix here is 1 by p. and the order of the matrix here is P by 1. A column matrix has one column and several rows, P by 1. So when it comes to matrix multiplication, you multiply a row by a column, not column by row. You multiply a row by column. And how do you multiply a row by column? You multiply corresponding components, then you find the sums of their sum. In other words, you find sums of products of
Excuse me?
corresponding elements. Sorry, yes?
Apple in the beginning,
Yes.
okay, we were using M and N for the rows and
Yeah,
yeah. Why are we introducing the P?
the P. Okay, so yeah, so these are dummies. So when you say the general representation of a matrix is M by N, but these are dummies. You know, M can be 2, 3, 4. You can even write it. You're not limited to M by N. It can even be K by L, depending on your favorite letters. But generally, we represent matrices with M rows and N columns. But the reason why I have used P here, it's because I want the number of columns in B to be equal to the number of rows in the number of columns in A to be equal to the number of rows in B, because that is the only way you can multiply. So you can only find products if the number of columns in A is the same as the number of rows in B. So the P is well chosen. You know, if I had M and N here, it means some of the elements will not have corresponding elements. But generally, we represent the order of a matrix by M by N. But it can be anything. M here can be anything. N can be anything. And you can have cases where N is equal to M. Anyone else?
Yes. And
Yes.
yes, madam.
Yes.
Hello.
Hello, I can
I
hear
have
you.
a question.
Yes.
I have a question.
Yes.
As we are going down simultaneously about the matrix. Matrix. I
Yes.
saw columns of 105, 132, 311, and now you have like I would like to put more clear and tell me where to do A and B.
Okay.
A and B. Yes.
Yeah, I understand. You know, I think our first experience with algebra was in primary school. And there's always this joke by people who don't like mathematics, and they will always make a joke that I've been finding X since I was in grade 4 in elementary level, and even now I'm at the university and I'm still finding X. And you're wondering, when will I ever find this X? So some people give up along the way, but what they don't realize is that they've been finding X all the way all through. So now, yeah, normally in algebra, whenever we use an arbitrarily, say, value, then it could represent anything. So we use the letters of the alphabet for general representation. So when I say A11, A11 can be anything. It can be 1, it can be -2, it can be 10, it can be even a complex number. It can even represent goats and cows. So it's just a general it's a placeholder actually representing an element. So for the general demonstration, we use arbitrary values. Then for demonstration purposes, we assign a specific value. So like if you notice the trend, especially in mathematics, you use X, Y, Z for representing arbitrary value. Then, depending on what you're working on, then you can assign a specific value. So therefore, if, for example, let's take just a real life case. Let's go back to a hardware case. I say that on day one, I sold A1 copper rods. On day two, I sold A2 copper rods. On day three, I sold A3 copper rods. So this is the general representation, and we use the general values when it comes to computations and on coding. So you have A1, A2, A3. That would be the sales for day one, sales for day two, sales for day three. But then I can now have the actuals. I know that on day one, I sold 1,000. On day two, I sold 3,000. On day three, I sold 4,000. So you first of all come with the general, where I use arbitrary letters in the alphabet to represent the values, and then you come back to the specific. And like in matrices, the general representation of a matrix is what we have up here. So we have, this is a general representation of the matrix. So these are placeholders. A11, it depends on what you have as A11 in your case. So like for example, in C here, A11 is 1. A12 is 3. A13 is -1. And then take the matrix C here. The general representation of a matrix is that it's an m by n matrix. So for C, what is the value of m? M is 3 and n is 3. It is a square matrix. If I take, for example, B, what is m? M is 3, n is 2. But you have the placeholder, the real values now, the exact values. A11 is 1. Like if I take B and I want to compare with the general representation of a matrix, then in this case I would say that I can say B11 is 1, B12 is 3, because I know B11 is the first element in the first row and first column of the matrix, first element in the first row and second column of the matrix, and so on. Okay, so is that clarified? So these are just general representation of arbitrary values. Then in your consideration now you can insert the specific values. Is that clear?
Yes.
Okay. Yeah, and then the lady who had asked about the
Yes,
just a,
yes.
the
Yes,
lady who
Peter.
had asked about just a
Very clear
minute.
now.
Someone
Yeah,
had
it's very
asked.
clear.
Yes.
Yeah, I'm seeing this now. It's very clear. Yeah,
Okay.
yeah,
Yeah.
yeah.
So, and that has been the problem. People hate maths because of finding X, but I think it depends on your attitude towards maths. Mainly depends on who was your maths teacher. Because if it is explained, then you not have a challenge understanding why we are using X and why we are using arbitrary values. Just a minute, I need to connect to power. Okay. Yeah, good. Candy, can you do one sample? Yeah. I, oh, that is forward for products. So I have, you see now, the best way and the easiest way to understand maths is to start with a general case and then we come to specific examples. And so I don't know what you're referring to with real values. Is that for multiplication? Can we do one sample with real figures? I think you're referring to multiplication. So, but I need to first of all demonstrate. So allow me to demonstrate, then you can come to to an example, but I think addition is okay. We're okay with matrix addition. We're okay with matrix multiplication of a matrix by a scalar. So we now want to look at matrix multiplication. You must start, first of all, start with the general before you move on to specific. And I said, when you multiply matrices, you multiply a row by a column. It's always row multiplied by column for matrices. So we first of all start with the row matrix. Say A11, A12, A1P. And then you have the column matrix B11, B21, B2P. And for these matrices to be conformable for multiplication, you must have that the number of columns in the row matrix should be equal to, this is P1, should be equal to the number of rows in the column matrix. So this is a matrix of order 1 by P. This is a matrix of order P by 1. So you can only multiply the row by the column if they are conformable. If the number of what do we mean by conformable? It simply means each element must have a corresponding element, because when you multiply matrices, you multiply corresponding elements, then you find their sum. For example, I'll take A11 multiplied by B11, A12 multiplied by B21, A1P multiplied by BP1. So each must have a corresponding element. And therefore, you must first of all, even before you carry out matrix multiplication, look at the number of rows and the number of columns and the number of rows. If they're not the same, then the two matrices are not conformable for multiplication. For example, let me take this row matrix. I have my row matrix 1, 2, 3. And I have my column matrix 2, 4, 0. And I want to multiply the two matrices, A multiplied by B. So to multiply A by B, I need to find sums of products of corresponding elements. So 1 multiplied by 2 plus 2 multiplied by 4 plus 3 multiplied by 0. And that would be equal to 2 plus 8, that is 10. And please notice, so this was a 1 by 3 matrix, and this one is a 3 by 1 matrix. The number of columns in A must be equal to the number of rows in B. And the resulting matrix would be of order 1 by 1. It only has one entry. If, for example, I take the matrix C to be the following matrix, 2, 3, can I multiply A by C? Can I multiply A by C? Is it possible? Can I multiply A by C? No. Why? Please give reasons. Why is it not possible to multiply A by C?
Because they don't have the same number of values.
Correct. Not the same number of
Or
values.
equal.
The number of columns in A is not equal to the number of rows in C. So please take, for matrices to be conformable for multiplication, so A and B are conformable for multiplication, if the number of rows, let me start with columns. The number, and ordering is important, the number of columns in A is equal to the number of rows in B. So that is the first thing we need to establish. If they are not, then the two matrices are not conformable for multiplication. Like for example, look at this example. Let's work out A multiplied by B in this case. So first thing, find the order of the matrix. So what is the order of the matrix A? What is the order of the matrix A? Nicodemus, you've raised your hand. What is the order of the matrix A?
Yeah, it's 3 by 2.
Okay, so the order of the matrix A is 3 by 2. How about the matrix B? What's the order of the matrix B?
2 by 3.
2 by 3. Now the question is, are the two matrices conformable for multiplication? Can I find A, B?
No.
Yes.
Can you find A, B?
Yes, we can.
Yes, we can find A, B because the number of columns in A is the same as the number of rows in B. How about BA? Can I find BA? You know, for BA now you'll have to write it as 2 by 3, 3 by 2. Is it possible for us to find BA?
Yes.
Yeah, it is possible for us to find BA since the number of columns in B is the same as the number of rows in A. So let's find AB in this example. So 1, let me write properly. So AB. So I have 1, 0, 3, 2, 1, negative 1, 3, 2, 1, 1. So then we are multiplying now. For multiplication now, you multiply. Remember we said you multiply row by column. That's the rule of matrix multiplication. So I'll take row 1, multiply by column 1. I'll take row 1, multiply by column 2. I'll take row 1, multiply by column 3. And that would give me the entries. So I have row 1 multiplied by column 1, row 1 multiplied by column 2, row 1 multiplied by column 3. Then I have row 2 multiplied by column 1, row 2 multiplied by column 2, row 2 multiplied by column 3. Then I have row 3 multiplied by column 1, row 3 multiplied by column 2, row 3 multiplied by column 3. So let's carry out now the computations A, B. So AB, so let me multiply row 1 by column 1. So row 1 by column 1 of B. So when you multiply a row by a column, you find sums of products of corresponding elements. So you have 1 multiplied by 3 plus 0 multiplied by 2. So the result here is 3. Then row 1 multiplied by column 2. 1 multiplied by 1, 0 multiplied by 1, 1. Then 1 multiplied by negative 1, 0 multiplied by 1, that's negative 1. Then 3 multiplied by 3 plus 2 multiplied by 2. So that is 9 plus 4. 11. 9 plus 4 is what? 13. Then row 2 by column 2. So 3 multiplied by 1, 2 multiplied by 1. Then you add 5. 3 multiplied by negative 1 plus 2 multiplied by 1. That is negative 1. Then I have 1 multiplied by 3. That's 3 plus negative 2, negative 1. 1 multiplied by 1 plus negative 1 multiplied by 1, that is 0. 1 multiplied by -1, that's -1 plus -1 multiplied by 1 negative 2. So you multiply rows by columns. So take row 1 multiplied by column 1, row 1 multiplied by column 2, row 1 multiplied by column 3, and so on. Okay, so yeah, so then this requires practice. But let me just let me see if there are more examples here where we can test. Yeah, so yeah, I just wanted examples where we can pick. Someone has a question?
Yes, I was asking,
Yeah.
what about a matrix of 3 by 3?
Yes.
Can we multiply?
You're
by 3?
multiplying a 3 by 3 matrix by which matrix?
By another 3 by 3.
Yes, it is possible. You can even have, like for example here, let's look at these matrices. Let's look at the 3. So this one is what's the order of this matrix? What's the order of the matrix A?
3 by 3.
So this one is 3 by 2. And this is a 3 by 2. Okay. And this is of order
2 by 3.
2 by 3. Now, let's look at these matrices. Can we multiply A by B? Are they conformable for multiplication? Can we multiply A by B?
No.
We cannot multiply A by B. Reason? What's the reason why? Why isn't it possible to multiply A by B?
Because the number of rows are not equal to the number of columns.
Correct. The number of rows in, you have to be specific. You have the preceding matrix. So you're looking at the number of columns in A and number of rows in B. You're looking at these two entries. They're not the same. So A and B are not conformable for multiplication. How about A and C? Can I find the product of A and C?
Yes.
So let's look how many columns do we have in A? We have 2, and you have 2 rows in C. So we can multiply A by C. Can you multiply B by A? So B by A, you have now to look at the preceding matrix. The preceding matrix is of the 3 by 2, and this is of the 3 by 2. Can you multiply B by A? Is it possible? Can you multiply B by A?
Think no.
Okay. Okay, so it's not possible because the number of columns in A is not equal to the number of rows in B. How about C by B? Can you multiply C by B? Can you find CB? So C is of order 2 by 3. And what's the order of B? 3 by 2. So it's possible to multiply C by B. And let's quickly find C by B. So I have -1, -1, 3, -3. And please you can be working on it on your own. So that is C. And then B is 4, 6, -3, 7, 6, and 5. So then, normally, if you find it difficult, I like looking at, first of all, writing it in general form. So I'll have row 1 multiplied by column 1 here. I'll have row 1 multiplied by column 2. The columns are for the matrix A, for the matrix B, while the rows are for the matrix C. Then I have row 1 multiplied by row 2 multiplied by column 1, row 2 multiplied by column 2. Then now you can compute them. So if, for example, now row 1 multiplied by column 1, that would be -1 multiplied by 4 plus -1 multiplied by -3 plus 3 multiplied by 6. Then row 1 multiplied by column 2, you have -1 multiplied by 6 plus -1 multiplied by 7 plus 3 multiplied by 5. Then come now to the second row. Row 2 multiplied by column 1. Row 2 multiplied by column 2. Multiply corresponding components, then you find their sums. Is that clear? Is it clear? So always check, are the two matrices conformable for multiplication even before you start multiplying? So for addition, we said they must be of the same order. So matrices must be of the same order. But you notice for multiplication, they are not of the same order. But as long as the number of columns in the preceding matrix are equal to the number of columns in the other matrix, the number of rows in the other matrix, then the two matrices are conformable for multiplication. So kindly take up this exercise. You can find all these values. And this is, I want you to, like, can I give you a few minutes to work on this? I want you to work on this because you want to establish. Notice that B is of order. This is of order 3 by 2. And then C is of order 2 by 3. So we have BC. So are the two matrices conformable? B and C, are they conformable? Can you multiply B and C?
Yes.
Yeah, the two matrices are conformable.
Yes.
So
Yes.
I want us to split
Yes.
into 2. Yeah, thank you. So B and C are conformable, so we can find BC. And how about CB? Are they conformable? Can you find the product CB? Can you find the product?
Yes, we can.
Yeah, it's because C is of
Yes.
order 2 by 3 and B is of order 3 by 2. So they are
Yes,
also
we can.
conformable for multiplication. So now I want us to split. So maybe if your name is in the upper alphabets, find B and C, BC. If your name is in the lower alphabets, those with alphabets like, let me look at participants. I see where so the A, B, and C's, we are the majority, A, B, C, D. Find the product BC, and then starting from Haron, H, J, K, L, M, N, and so on, all the way to Wycliffe, find CB. So the ABCs, you find the product BC, and the others, Jacqueline and the Rachels and the others, you find CB. Then you want to compare. You'll give us the entries of BC, and then and give us the entries of CB. And I want you to type the matrix as follows in the chart. If, for example, you want to type a matrix C in the chart, so you just write them like this: 6, 10, put a semicolon, -3, 0, 10, put a semicolon, and then -1, 0, -5. That way I'll be able to pick the entries. So the upper alphabets find B and C. The lower alphabets find CB. We want to compare B, C, and CB. Then once you're done, you can type the answer in the chat. So I'll give you 5 minutes. 5 minutes are enough. So we are multiplying B and C. So B and C are on the screen. So multiply B and C. So 5 minutes it means because I still want to cover determinants. So I want to cover the entire module today. So I'll give you 5 minutes. So the upper alphabets you're working out BC. The lower alphabets from J downwards you're working C, working out CB. Then you give me the answers. Okay, so thank you. I can see both answers have come through, and they're actually correct. So we tested on. You can actually compute the answers on Maxima. So this is what I had. So we verified the answers. So what you do if you are to solve these on Maxima, so for those of you that have managed to install Maxima, you can quickly text. So first of all, you enter the matrix. So the matrix B is 3 by 2. And then you give the entries. So the entries are 4, 6, -3, 7, 6, 5. And then we can enter, so that's the first matrix. Then we enter another matrix. C is 2 by 3. Then you have -1, -1, 3, -3, -2, and 2. So you have the two matrices, I5 and I6. So we want to multiply B and 6. So go to multiply matrices. So this was input 5. We are multiplying by input 6. And you have the answer there. Then you can still multiply input 6. That will be CB multiplied by input 5. And you have the answer. So you can use Maxima to verify your answer. Okay, so yeah, that's okay and very well done. I'm happy with the results that we've gotten. It shows that we've understood matrix multiplication. But what is your observation? B and C, in general, when you multiply matrices, A and B, is it true that A would be equal to BA? When you multiply matrices, even if it was a square, let's take a square matrix. Let's take two square matrices. Let me write them down. Let me take two square matrices. Let me take B and C. We multiply, or even take A and B here. So we'll just quickly multiply with Maxima and we'll see what happens. So this is 8. I need to write it down so that I can enter. 85272 565. The other one is 3, 10, 6, 5, -1, 7, 2, 2, 10. 3, 10, 6, 5, -1, 7, 2 to 10. 852272565. So let's put this on Maxima and see how it behaves. Where was I? Share. Yeah, so we enter matrix. So let's start. It's a 3 by 3. So 3 by 3, that is 8, 8, 8, 5, 2, 2, 7, 2, 5, 6, 5. So that's input 9. Then we enter another matrix. So 3 by 3, 3, 10, 6. then 5, -1, 7, then 2, 2, 10, 3, 10, 6, 5, -1, 7, 2, 2, 10. Okay, so that's input 10. So let's see what happens. So we multiply the matrices, that was input 9 by input 10. Okay, so we have the answer there. Then let's look at the other way. Input 10 multiplied by input 9. So what's our conclusion? We have sampled too. We have sampled with a square matrix and we have sampled with two matrices of different orders. So what's your take when you multiply matrices? Are they commutative? Is multiplication of matrices commutative? By commutative, we mean when I multiply A and B, will it be equal to B multiplied by C? Is it commutative? Is matrix multiplication commutative? So it is non-commutative. It's not commutative. So BC is not equal to CB. In general, matrix multiplication is not commutative. Matrix multiplication is not commutative. Matrix multiplication is not commutative. Okay, Tracy, you've raised your hand.
Thank you for that. So BC is not commutative to CB,
Yeah.
but does it also mean that if can BC always be correspondent to CB?
That BC is equal to CB.
I don't know.
That is your
Like
question.
compatible. Like can they always be multiplied?
No, it depends. You see, like, for example, that's a good question. You can have,
It well.
yeah, you can have, say, let me think of a good example. You can have 1 by 3, 2 by 3. No, 3 by 2. Okay, 3 by 2. So A is of matrix 1 is of order 1 by 3 and B is of order 3 by 2. Are these two matrices conformable for multiplication?
Yeah, yes.
So they are conformable for multiplication since the number of columns in A is equal to the number of rows in B. How about B and A? Are they conformable for multiplication? Tracy, are they conformable for multiplication?
No, they're not.
They are not.
Why?
Since this is of order 3 by 2, this one is of order 1 by 3. The number of columns in B is not equal to the number of rows in A. So you can have a case where A and B are conformable for multiplication, but B and A are not conformable for multiplication.
Okay, thank you.
Okay. So always look at the number of rows, the number of columns in the preceding matrix against the number of rows in the second matrix, left and right matrices. Okay, so I think that's okay. So I want to cover the last. I know it's already 10 past 10, but we started late. So give me like 30 minutes or less. We look at the determinants. And then let me see the extent of determinants so that I don't cover concepts that will be covered in linear algebra. So let me see what I'm supposed to cover. Applications, you can look at them. Does it look at the minor cofactor method? I think this would be important because you need determinants of 3 by 3 matrices. So let me see how they were computed. Or we just use Yeah, we need the minor cofactor
Excuse
method.
me, I have a question.
Yes.
How do we type the answer for, like, example of BC that we did? Now, when inputting the answer, what's the best way of typing it?
Normally what we do, if I give you a problem that has matrices, I'll give you the boxes. Like if you look at the quizzes, you'll have boxes where you just key in the values. We will not require that you type the matrix. Because you remember stack, you're asking about answering a question. Now, if you want to input a matrix in your answer,
Yes,
is that your question?
especially,
Yeah.
yes, that's my question, especially an answer like for BC where we have three dimension.
Normally, if you look at the quizzes in the course, we'll give you boxes where you just insert values directly. Like model, end of module quiz. Let me see if there's a question on data. So you'll have you'll just enter the values in the box because Stack has been built around Maxima. So you've seen how I was entering the values in Maxima. I didn't have to write the matrix as it is and I'll just get an output. That's the same tool. Stack works behind Maxima. So it uses Maxima. So let me see. Let's preview this one. I hope it has a box preview. Yeah, so you just will give you boxes where you input the values. So you don't have to type the matrix.
Okay.
Yeah. But can you see this? This is how we input matrices, but we're not going to require that you input matrices in Stack because already it has been embedded with Maxima. So you just have to put in the values into the boxes and it will automatically pick the values. But this is how you type a matrix in Maxima. Can you see this? Can you see matrix, open brackets, close brackets? That is how you input a matrix in Maxima. And this is the output. So like, say, let me see if this is going to work. A to be the matrix. One, two. Yeah, common. But you don't have to go through this because you already have a toolbar that can quickly give you the output. So you don't have to type it manually. Control Enter. No. What did I miss? Oh, it's not capital. It's small m. But you don't have to go through all this because you have a quick tool that you can use to input the matrix. And normally in Maxima we use a colon for equals. So B equal to the matrix. But Stack will give you the boxes where you just enter the values in the boxes. 3, 4. Let's see. Yeah. So that is how you type a matrix in Maxima. But you don't have to go through all this because you have the quick tools. You see, you have all these, you find the transpose, you come back and even find the determinants and all that. Remember even that module 4 where we were finding roots of polynomials, you can verify your answers here. The roots of a polynomial, find the roots, solve a linear system. I think there was a point where we were looking at quadratic inequalities, You can always verify your answers calculus, we'll look at it later. For those of you that are taking Math 103, you can verify your answers. Quick access tools have been given. Okay, so allow me to cover any questions. I want to cover determinants. Are there any questions so far?
So we need to install the stack.
No, you don't need to. Stack is for question authoring. And
Maxima?
unless if you want to learn how to author questions, then you can. And you cannot, because Stack is Moodle based, unless if you have access as a lecturer on Moodle. Maybe teachers are interested. If you have a Moodle, if you have a teacher in the platform or someone who is teaching maths elsewhere, then if you have a Moodle platform, then you need to install the Stack plugins, because Stack is a Moodle type question. So you can author a question. Can you see what I have here? So this is how you author questions in Stack. So this question has been authored, but you need to have the Stack plugins into Moodle to be able to author such a question. But for using Maxima for your computations, then you can install Maxima into your computer, and it's open source. Maxima is open source, so you just need to go to your browser and search Maxima. Search Maxima, and then it's from here, Maxima. It's a computer algebra. It's just like a calculator, but now more advanced. So Maxima, and it's open source, so you click on it, and then where is the download option? Option. Maxima, where is documentation? Click on a version to see. No, these are the number of changes. Why is this one taking me here? I need to go to downloads. Let me see. Yeah. So once you get here, then you can download. If you're using Windows, if you're using Mac, if you're using Linux, then you can choose the version that works for your device. Then once you've installed, then if you want to understand more on how to use Maxima, we have Maxima documentation. So then there's a quick link on our module 0. So introduction to Maxima, symbolic mathematics using Maxima, rules and patterns in Maxima. There's so much you can do with Maxima, not just as a calculator, but there's so much you can do with Maxima. So you can look at the documentation and read through. Okay, but there's a manual with various functions for use. Okay, so let me see this. Yeah. And you see, like now this one gives you a hint on how to sketch graphs in Maxima. Yeah, there's so much you can explore, but it's very easy to install. It doesn't cost anything. It's open source. You can use it as your calculator. It's simply a calculator on the desktop, but an advanced one. So you can use it to verify your answers. If you want to visualize some graphs, you can use it, but you can also use GeoGebra to visualize graphs, especially when we come to conic sections, we shall use GeoGebra. So any questions, please allow me to look at determinants. I don't want to leave this module hanging. So please allow me to look at determinants. Determinants are not new to us. So allow me to look at determinants. If there are no questions, are there any questions so far?
Please, one more.
Okay.
How do you find the product of matrices on Maxima?
Or products. I already did that. Where is it?
I think I missed that.
Yeah. So what you do, you input the matrix first.
Yes.
So you can see like here I inputted the matrix, and you just go to the toolbar. You see matrix, where there's a matrix. There's an icon for matrix. Click on the icon, enter matrix. So first of all, since you want to get the boxes, you must enter the order of a matrix. If it's a 3 by 3 matrix, if it's a 2 by 2. Oh, it's not moving.
I've already done it, yeah?
Okay, so yeah, so you enter the matrix. So You've entered the matrix, choose the order of the matrix, then enter the values of the matrix. So normally in Maxima, you'll always have these two. Can you see percentage I1 and percentage O1? Percentage I1 means input output, that when you input this function, this is what you get as an output. Input output, inputs output, and then you have the answer. And then now to multiply matrices, so still go back to the toolbar, click on matrices, then click on multiply matrices. And now input, so I want to multiply I1 by input 2, because you've inputted the two matrices. You have the two matrices you want to multiply. Then you click OK, and it gives you the answer. So you're multiplying input 1 by input 2. And you can go back, multiply matrices, then now multiply input 2 by input 1. Then OK. Is it clear now?
Yes, thank you.
Okay.
If the inputs cannot be multiplied, to give you an error.
Yeah, it will give you an error. Yeah, and you can even try. We can try. Like, no, let me leave you to play around. It will give you an error because they are not conformable. So it will not be able to multiply because it's matching. And this is the reason why we are looking at the theoretical approach. So that, because you are looking at future developers. So someone who will look at Maxima and feel like it's not efficient. Can I improve Maxima? And you'll have another version of Maxima, an improvement of Maxima. So, but you have to understand the theoretical and understand how the computations are being carried out and now propose a change, because you're looking at innovations and introducing new tools that can be useful. Okay, so let me introduce determinants. Determinants are not new to us, but the question is, why do we need determinants? Now, if I have a square matrix, determinants only apply for square matrices. Number of rows equal to the number of columns. And normally we represent a square matrix, the order of a square matrix by n by n. But you can see write it as m by n, p by p, whatever, t by t, depending on your favorite letter of the alphabet. But in general, we use n by n for square matrices. The number of rows equal to the number of columns. And so you can have a matrix that looks like this. I know students don't like it when I use A11, A1n. But you have to use the general case before coming to a specific case. Otherwise, if I write A equal to 1, 2, 3, a learner will interpret that that is a square matrix and they'll be using the same values all through, which is wrong. But you have the general representation. Now, in some cases, you'll have a very large square matrix. You can even have a 1000 by 1000 square matrix. For example, Google search engine and even ChatGPT, ChatGPT just collects data from all over and draws a correlation and gives you a summary after checking all over. So, for example, the Google search engine is a very large matrix. You are collecting different values from here and there, and you want to give an input. And so in some cases, you find that you're working with a very large matrix. Like you can search the size of the Google search engine matrix. It's a very large matrix learning to millions of digits. So, but it's a square matrix. So if you're working with a very large square matrix, even 4 by 4 is a large square matrix. You saw me struggle with writing a 3 by 3 matrix. Imagine if I have to write a 4 by 4 matrix, 5 by 5 matrix, 6 by 6 matrix. That's a very large matrix to work with. And therefore, when you're working with square matrices, regardless of the size, it's always important to look at a representation of the square matrix. And what is a representation here? Can I find a scalar that represents the matrix? That working with a matrix A is the same as working with a scalar K. So that instead of inputting A, I'll just input the scalar to represent my matrix. And there are several functions that can help us do this. One of the functions is the determinant. Later on, we shall look at other functions, other scalars that can be used to represent a matrix. So the determinant is a scalar representing a matrix. And if I know the determinant of a matrix, there are so many things. The determinant tells me so much about a matrix. When the determinant is negative, when the determinant is 0, I'll know what that means. So there are a number of applications based on determinants of a matrix. So can I find a scalar to represent the matrix so that from the scalar, I can tell more about the matrix, or the scalar can make computations involving the matrix much easier. And this is where the determinant function comes in. And at your all levels, you are introduced to determinants of 2 by 2 matrices. If, for example, let me just to test your prior learning, if I have a matrix 1, 2, 4, 3, what is the determinant of the matrix A? So what is the determinant? What is the determinant of A? I just want to test our prior knowledge. All of us have gone through O levels and you are introduced to determinants in O levels. So what's the determinant of A? Apart from maybe those who cleared school recently, but I don't think they have scrapped determinants because right now they are covering determinants even in junior school. So I don't think it has been struck, it was struck out of the curriculum. So the determinant is -5. And how did you find -5? Anyone who is willing to switch on their mic and explain to us how we find -5?
1 times 3 minus 4 times 2.
Okay, so you multiply the secondary row by the product of the primary row, then you subtract the product of the secondary, diagonal, primary diagonal and secondary diagonal. Okay, so now, okay, so let's leave it as it is, because I would have explained why secondary row versus but I don't want to take you through that. But if I was teaching the mathematics and computing group, then I would have to explain why that is the case. So
What
you have,
if you wanted to find a determinant?
pardon?
What if you were to find the determinant of a 3 by 3 matrix?
Yeah, let's chew the baby food first, then we'll go to the hard food. 1, 2, A2, 1, A2, A2, 2. So to find the determinant of these matrices are 2 by 2, then the determinant would be the product of the entries in the main diagonal minus the product of the entries in the secondary diagonal. But if A is a 1 by 1 matrix, no, you don't use squares. So determinant of A to 2. So normally determinant is denoted by det of A or just A between bars. And if it was a 1 by 1 matrix, the matrix is just A11. Then the determinant of A would be equal to A1, would be equal to A11. Okay, so then now someone has asked about 3 by 3. Now, to find the determinants of 3 by 3, and this is where I need to get your attention. So we use what we call the minor cofactor method. So we use the minor cofactor method to find determinants, actually determinants, even for a 2 by 2 matrix. And what do we mean by the minor cofactor method? Let me use the example of a 3 by 3 matrix. So the matrix A has entries A11, A12, A13, A31, A32, no, sorry, A21, A22, A23, A31, A32, A3, A33. So now this is a 3 by 3 matrix. So first thing, to find the determinant of this matrix, then we choose our pivot row. So you can choose your pivot row or column, but in this case we choose our pivot row. So let row 1 be the pivot row. Then the next step is you find the minors. And how do you find the minors? You find the minors. So the minors corresponding to the entries in the pivot row. So the minors corresponding to A11, the minor corresponding to A12, and the minor corresponding to A13. And we denote the minors by M11, M12, M13. So how do we find the minors? The minors would be obtained by deleting the ith row and jth column. So for example, the minor now corresponding to A11, I delete the first row, first column, so that M11 in this case would be A22, A23, A32, A3, A33. Then we have the minor corresponding to A12. Delete the first row, second column. So delete first row, second column. So we are left with A21, A23, A31, A3, A33. Then M13. Delete first row, third column. A21, A22, A31, A3, A32. So first thing, fix your pivot row. It doesn't have to be row 1, but in my case I've picked row 1, standard. So pick your pivot row, then find the minors corresponding to the entries in the pivots in the pivot row. And you obtain the minors by deleting the ith row and the jth column. Like for example, M11, delete row 1, delete column 1. So this becomes your M11. For M12, delete row 1, column 2. And so this would be the entries of M12. M13, delete row 1, column 3. And so you have A21, A22, A31, A3, A3, A32. And so then, after you've obtained the minors, the next step is whereby you obtain what we refer to as the cofactors. The cofactors now would be denoted by capital Aij, would be -1 raised power I plus j multiplied now by the determinant of Mij, the determinant of the cofactors. So for each of these entry, we'll have the corresponding the M in the determinant of the minors. So for each of the entries in the pivot rows, we'll have the corresponding cofactors. So first of all, find the minus, then the next step, find the cofactors. After we found all those values, then the determinant of the matrix A will be the sum of all of them. So our fixed I, so J is varying from I to N. I here is fixed because you fixed a row. So then you have Aij multiplied by capital Aij. That now becomes the determinant of the matrix. So if it was a purely mathematics class, I would explain why we are doing all this. It has something to do with permutations and signs of a permutation and all that. But this is all we need. So first of all, find your pivot row, identify the elements in the pivot row, find their minus, after which you now find the determinant of the minus, and from the determinant of the minus you have the cofactors. And this function is very important, -1 raised to power I plus j. After you successfully found all the cofactors, then find the sum of these products should give you the determinant. Now, let's go now to the practical. So let's just pick an example and find the determinant now over 3 by over 3. And I can even start with just a simple one, a determinant of 2 by 2. Because the method applies to all matrices, to all square matrices. Like for example, let's work with the matrix A here. Let's start with A, then we'll go to a 3 by 3. So first step is fix. So I'm fixing the fix I to be equal to 1, meaning that I'm using row 1 as my pivot. So I have A11 here is 5. I have A12 here is 6. Next step is to find the minor M11. Delete the first row, first column. Delete first row, first column. So M11 is a matrix, -2. It's a 1 by 1 matrix. Then find M12. Delete first row, second column. So this is the matrix 3. So those are the minors. Then next thing is to find the cofactors. A11 would be -1 raised to power 1 plus 1, determinant of M11. And A12 would be -1 raised to power 1 plus 2, determinant of M12. And the answer here is, what's the determinant of M12? It's just -2. And then A12 here, A12, the determinant of M12 is 3, but this is -1 raised to power 1 plus 2. So equal to -3. So that now determinant of A will be summation j equal to 1 up to 2, I fixed, I equal to 1 fixed, of Aij, so that you're simply taking A11 plus A12, which is, what is A11? A11 was 5. 5 into -2 plus, you see why we were subtracting, 6
Excuse me, as you go on, please.
-3. Pardon?
What does I and J denote?
I denotes row. Ith row, jth column. When I write Aij, ith row, jth column. So we always use I for rows, J for columns. So in this case, this is just general. You can see I'm varying. J equal to 1 up to 2. I is fixed, meaning I'm writing A11 when J is 1 and when J is 2. But I is fixed to be equal to 1. Is it clear?
Oh, yes, you say I is row, J is column.
Yes. Always I represent the row, J will always represent the column. That is the standard notation when it comes to matrices. Any question?
I'm curious,
Yeah.
where do we apply the unit vector?
No, it's no. You see, now we are mixing things up. We used an I in matrices. No, we used I in complex numbers. So when you talk about now, when you I and J in vectors now would represent the unit vector and the unit vectors depending in the plane. But now we are using I here in the context of rows and columns. So the I here is not for the unit vector. It's just a position for the rows. It's just a position for the rows.
Oh.
Is
Okay,
it? Pardon?
from this example you've given,
Mm.
can you repeat from where you are now getting a determinant of A by using the summation?
Yeah. So now, the general function for determinant, I'll have to clear this, but I didn't want to clear, but let me clear. Determinant of A would be summation J equal to 1 up to, and because you're varying the columns, I fixed Aij, capital Aij. So if I'm working with a 2 by 2 matrix, I varies, there are 2 rows. So I varies from 1 to 2 and J also varies from 1 to 2. So if I'm working with a 2 by 2 matrix, so for this example, determinant of A would be summation J equal to 1 up to 2, I equal to 1 fixed. Aij, capital Aij. So I'm fixing I equal to 1. So this would be the same as summation J equal to 1 up to 2 A1J, capital A1J, because I've fixed I equal to 1 all through. Then I vary the J's. So this would be A11, A11, that is when J is equal to 1, plus A12, A112. Is it clear now? Is it clear? Let me work on a 3 by 3. I wish you did confirm. It's feel free to say no so that I can know which other example to give.
No, when you're putting that summation, there's that value too. You are putting there. It's not very clear how you are getting.
These two. J
Yes.
equal to 1. Okay, now I know where the problem is. If I'm adding, I have this sum. 1 plus 2 plus 3 plus 4 plus 5. I can write this sum in summation form as summation k equal to 1 up to 5 of k. Okay? So that I can always take it back. When k is equal to 1, I have 1. When k is equal to 2, I have 2. When k is equal to 3, I have 3. When k is equal to 4, I have 4. When k is equal to 5, I have 5. Now, coming back to this, when we say J, these are natural numbers. J's and I's are natural numbers. You know, the natural, ordinary counting numbers. I equal to 1, 2, 3, 4. So when you say you're summing J equal to 1 to 2, you're considering natural numbers between 1 and 2. And there are only 2. When j is equal to 1 and when j is equal to 3. If I write summation
So
j equal
it's
to
like
1 to 3, aij, capital Aij, then I'm summing over natural numbers between 1 and 3. So I'll consider j equal to 1, j equal to 2, and j equal to 3. So it's going to be I1, I2, AI, no, I11, AI2, A capital AI2 plus AI3, capital AI3. Is it clear now? Is it clear now, the explanation on the summation, on what the summation means?
From my understanding, it's maybe can say a range of values of j.
Yes,
Where j
natural
falls from.
numbers, yeah, natural numbers.
Natural numbers. But from our example here,
Yes.
from our example where you said example 8, let A be 5, 6, 3, 2. How did we determine the range of the natural numbers there to say it's between 1 and 2?
No, you see now the range here gives us the number of columns in the matrix.
Oh,
I represent
okay.
rows, J represents columns. So if it is a 2 by 2, I will range between 1 and 2 because it has 2 rows. How many columns? 2 columns. So it's between 1 and 3. If it's a 2 by 3, 1 and 2, sorry. If it's a 3 by 3, it has 3 columns. So J should range between 1 and 3. But remember, I is fixed because we chose the pivot row when it comes to the determinant function. Is it clear now?
Yes, it's getting clear. Only that when we say I is fixed, and we say the I is the number of rows, right?
Yes.
So from this example, we have 2 rows.
Yeah. So yeah, we have 2 rows.
So I will always be 2. Or
No, you see, let me start with. Let me start here. Let me start here. Before now, I move to. You see, yeah, this is our matrix. So the matrix is an array of numbers. So in this case, the matrix has m rows and n columns. And so among the m rows, you can pick out one row. We call it the ith row. So like, for example, this is row 1. So when I is equal to 1, we have row 1. When I is equal to 2, we have row 2. When I is equal to m, we have row m. So I will range between 1 and m. That will be the range. I don't want to use that. I just want to use, let's just use the list, the index. So I will range between 1 and m. So you have m rows, but you can have the ith row. Row 1, row 2, row 3. The same case applies to columns. In total, we have n columns, but you can pick the jth column. Say, for example, column 2 becomes now, we have column 2, and somewhere here we'll have the jth column. So the I and the j represents in general the positions. So it is actually the index now for the rows and columns in the matrix. So you have row 1, row 2. And the other way of writing this matrix, you can write it in this form. A, I, J, M by N, meaning that the i's range between 1 and m, and the j range between 1 and n. Or in other words, we have m rows and n columns. And you can pick the position. Like for example, I can write the ith row. I can write the jth column, or write row 3, row 4, and so on. So the i's and the j's are just the index of the rows in the matrix representation. If, for example, I take this matrix, if I take the matrix, just take any, I can even use this B. The matrix B. The matrix B is of order 2 by 3. So, but I can have the index for the rows. The index for the row, the general index for a row is I. In this case, either I is equal to 1 or 2, because there are two of them. J is equal to 1 or 2 or 3. That would be the index for the column. So either J is equal to 1, 2, or 3. So, but now when it comes now to the determinant function, so with the determinant function, you fix a row. And that is where we have to fix which row. We are taking I equal to 2. When I say I equal to 2, it means I'm fixing row 2. But for generally we fix row 1. So I'm fixing I equal to 1 fixed. It's easier when you fix row 1. It's easier to find the minus when you fix row 1. So you have fixed the ith row to be equal to 1. Then you vary the columns. J equal to 1. We cannot find determinants of these matrices. It has to be a square matrix. J equal to 1 up to say 3, assuming that it's a 3 by 3 matrix. So it means you're varying J over 3. So if I write AI, if I fix I equal to 1, and assuming that A is a 3 by 3 matrix, if I fix I equal to 1, the other way of writing the determinant is A1. I didn't want to do that. A1J, A1J. So that I equal to 1 is fixed and you're varying J over 3. So consider J equal to 1, that is column 1. Consider J equal to 2. Consider J equal to 3 and find the cofactors. But if I have not fixed I can still write the determinant to be Aij, capital Aij, J equal to 1 up to 3, I fixed. You see, here I have not specified the value of I, because it's not mandatory that you fix I equal to 1. You can choose to fix I equal to 2, provided you are able to find the minors and the cofactors. You can even fix it to be 3. It doesn't have to be equal to 1 all the time. So it depends on your choice. But for general representation, we fix the first row. I think, have I made it more difficult, or is it clearer now? Is it clear now? Is it clear now?
Yes.
Okay. Yeah, great. So let's go. Note, you can only find determinants of square matrices. You cannot find the determinant of this matrix. Always square matrices. So you only find determinants for square matrices. So let me work out a 3 by 3. I don't like determinants of 3 by 3. It's cumbersome. But let's just work it out. But we are going to verify the answer. Now, taking this example, we need to first of all fix a row. And we fix a row. And your choice of row should be that row that has many zeros. Let me complicate it a bit, because this has been computed with fixing row 1. Let me complicate it and fix row 3 instead. Normally, you look at the row that has very simple values and that has zeros, so that you have fewer computations to perform. So I fix my row. So I'll fix I to be equal to 3, meaning that I fixed row 3. So then, next thing I'll write down the elements in row 3. So I have A31 is 4, I have A32 is 0. I have A33 is 9. Okay? So I've fixed the pivot elements. So I fixed my row to be I to be equal to 3. So we fix the pivot elements A31, A32, and A33. After you fix the pivot elements, now find the minus M31. How do you find M31? Delete the ith row, delete the third row, first column. Delete third row, first column. So you're left with the matrix 6, 5, 7, negative 1. Then M32. Delete third row, second column. Delete third row, second column. So you have 2, 5, 3, negative 1. Then find M33. Delete third row, third column. 2, 6, 3, 7. So we have found the minus. So the next thing is to now find the cofactors. The cofactors would be, let me write them on this side because of space. So you have negative 1 raised to power 3 plus 1, determinant of M3, 1. Then I have negative 1 raised to power 3 plus 2, determinant of M3, 2. Then I have negative 1 raised to power 3 plus 3, determinant of M3 and 3, 3. So these will be our minors. This is A31, A32, A3, 3, 3. So what's the determinant here? This is where now I go to maxima very fast. So M31, I need to find determinant of M31. So that's negative 6 minus what? Minus 35, negative 41. But I have raised to power 3 plus 1, so that becomes 41. Then I have negative 2 minus 15, negative 17. So that becomes positive 17 because of 3 to power 2. Then I have 14 minus 18, negative 4. So that's negative 4. So I have my minus now. So what's going to be the determinant? Determinant of A will be summation j equal to 1 up to 3 because there are 3 columns. Aij, capital Aij, I fixed. But in my case, I've fixed I equal to 3. So in our case, the determinant of A would be a summation j equal to 1 up to 3. I've fixed I equal to 3. So this would be A3j, A3j. So that now this one becomes A31, A31 plus A32, A32 plus A33, A3, A33. Because in our case, we fixed I to be equal to 3. Then we substitute and multiply. So this would be 2 into 41 plus, no, sorry. I didn't even have to find M2 because 4 is 0. So this would be, A32 is 0, so I didn't have to find that. So this would be 4 into 41 plus 0 into 17 plus 9 into negative 4. And then you can verify the answers. Is it clear? Is it clear now? Any clarification needed? You see, you don't have to fix I equal to 1 always. You can choose. You can even try the same examples and fix I equal to 2 or fix I equal to 1. And you find that regardless of your choice of row, the answer is always the same.
Just a little clarification.
Yes.
Small a and capital A.
Yes.
Capital A denotes the determinant of A.
No, which capital A? This one.
Yeah. Yeah, when you are getting the summation from the formula, summation is equal to A 3J,
The
then
capital
capital
A,
A.
Aij here are the cofactors. The cofactors. You see these values I'm finding here are the
Yeah.
cofactors.
And now small a.
Small
J.
a is a pivot, the pivot element. Can you see them here?
Yes.
The pivot elements.
Yeah.
Is it clear now? Clarified?
Yes.
Okay. Now I want to leave you to practice. I don't want to find determinant of another matrix. You can always use maxima or even your calculators to verify whether your answers are correct. So then after that, now we can applications of areas in finding of determinants in finding areas of geometric figures and also finding volumes. This one you can read on your own and understand because it's application. Just being able to find the determinant of a matrix, you can find the area, and you can also find the volume. Because volume is normally given by cross section. Like I can have a parallelepiped here. Just extend this. So all I need is the area, the cross-sectional area multiplied by the height. And the height here will be the length of this vector. And then that gives you the volume. So, but in this case, the formula has been given, the formula for the area without derivations, because you're keen on the applications. And then, and then more exercises for you to attempt, then the facilitated tutorial problem. I want to finish because I have a meeting starting exactly at 11. So can I hold the questions for next week? If there are any, please now revise. I think I've given you an overview. Engage, discuss with one another. But if it's a burning question, you can always reach out to me. Any questions so far? Okay. So please practice, try solve as many problems as possible. Watch the YouTube videos. I think the YouTube videos are nicer. But at least it's good to have eye present so that we can give our course the human touch. But there are so many YouTube videos, like finding determinants, they are here. Okay, multiplying matrices. I think this person has a better handwriting than I, so you can watch finding determinants explained. But if you need any further clarification, and you're not limited to these videos, I just sampled a few from YouTube. So you can go back to YouTube, and this has been a while. We did this content in 2023. So most likely there is new content and new and nicer videos. You can look out for videos in Khan Academy. Khan Academy does very nice videos which you can watch. The other one, what is it called? Yeah, some free courses in edX, so you can explore. Someone was speaking.
The videos you sampled were done by blacks or the whites. The whites speak very fast.
The Indians. So, but actually, Indians have done so much I think, because of, you see, the Intragandhi Intragandhi National University. UNISA was the first open university. So you find that it's either the white people from South Africa or the Indians because of the Intragandhi National Open University. But now we have some from edX, especially because of Open University of UK. Yeah, but just try. The beauty with recorded, you can always replay, pause, replay, push back, rewind. Yeah, so you can always do that. But we also give it a Kenyan touch with, I think Kenyans, we are so, like I would have, my plan when we operationalized the university was that I'll be able to pre-record as many videos as possible before we start. But we found ourselves with a lot of work. We are still establishing systems in the university. So, but the future for OUK is that we shall have Kenyan lecturers being able to pre-record sessions. So that's our vision, and it will be very soon because once we are done this year, the university will be fully operationalized. All the structures will be there, and then we'll be free to do what we are called to do. That is to facilitate learning, and so expect more materials to come from the faculty at the Open University of Kenya, and also from faculty within the Kenyan region. Yeah. Okay, so let's call it let's end there. My other meeting is starting in a few. So let me end there. Then let's keep engaging. If you have any questions, feel free to ask. But peer-to-peer support is the best. Peer learner-to-learner support is the best. So kindly, if one of us is stuck, let's support them. Don't shy. Ask even the simplest question on the WhatsApp wall. You might think your question is trivial, but it's important, it's relevant. So let's engage on the WhatsApp wall and also on the discussion forum. Otherwise, thank you, and thank you
Excuse me,
for your
Mwalimu.
participation.
Before you leave,
Yeah.
I have a problem accessing the recorded videos on Panopto.
I
I can't
don't
seem to.
put, mine I don't put on Panopto. Is
Oh,
it
where
for
do
this
you
course or another one?
for this course?
Yeah, I don't put on Panopto because I realized it's not loading some of my videos. It has not loaded any actually. So what I do, like for example, immediately after I finish this session, I'll come to the end of this module. Just right at the end here, I'm going to add the recordings. So if you look at all the previous modules, starting from module, even starting from introduction, I have an introduction video where we did the introduction of the course here. If I click here, okay, inanipeleka kwa nini? Sorry. Yeah, if you click there, you see the recordings are here. So you just need to copy the passcode and then paste it. That was the
That's the
introductory
typical.
session. The introductory session, and I did morning and evening. Then come to module 1, just right at the end of module 1, you see it here. So you have the recordings. Copy the passcode, enter. Go back, module 2, at the end, the recording. Module 3, at the end, there's a recording. Module 4. Module 5, we did the evening and you also did Saturday. So you have these 2 recordings. Module 6, I'll add a recording. Immediately it's loaded, I'm going to add it today. You'll find it here. Okay?
Okay, thank you.
Sawa sawa. Okay, others, thank you, and thank you for your participation. Let's meet. Please bear
Sorry.
with me. Pardon? Pardon?
Dr. Beth, mine is really quick.
Okay.
Can you hear me? Okay, the exams we know are in May. So do you know the tentative time? Like, is it mid-May, beginning of May, or end May?
No, for exams.
Yes.
I'll share the schedule. I think the schedule was circulated. You might have missed it out. But I'm not sure of the dates, but it will be, well, currently we're in week 7 of learning, meaning that that would be mid-May or towards end of May. But I'll look at the dates. We have the dates. The dates were shared with the students. I'll retrieve and put it on the Mat 101 wall. And if someone has it, if anyone has the schedule, because it was shared with the students a while back, you can put it on the wall for those who missed it out. So in case I forget, because right now I'm going into a meeting, but if anyone has the schedule, they can post it there. But that should be 4-5 weeks from now.
What happens when one misses the first set of exams?
You take exams when you're ready. If you miss this series, the coming series of exam, you can take the next and the other one. You take exams when you're ready. And ready means you have completed all the learning activities.
And the fees?
No, fees is not mandatory for now. What will happen is that you not see the results. You not see the grade you got. You only get the remarks. It's a pass or fail without a grade because you not paid fees. But you not we are not going to restrict. Pardon?
How often are the exams produced? For instance, if there's
Every
one
2 months.
every 2 months.
Yes.
Okay.
So after May, we shall have another series of exams in July, thereabout, for the specials. So if you miss the May exams, then you can take the August exams. But we give you a flexible fee payment plan, but try and at least complete fees before the exams. But if you're not able for some reasons, then you're advised to make sure by the time you're completing an academic year, then at least make sure you have paid the fees. Allow me to drop. Yes, but for now, but the systems are now going into place. So maybe for May, but for July, all the systems will be in place. It's only that we've not merged the LMS with the fee payment. But once the systems are in place, then you'll be restricted. But for now, we allow you to take exams before paying fees, but you'll not be able to see the results. Yes. No matter which row or column I choose to expand along using the cofactor, it will be the same. You can even fix a column. I didn't want to confuse you. You can fix a column. For those of you can practice, Instead of varying the j's, you now vary the i's. So your formula will now be I equal to 1 up to n, j fixed. You can fix a column or fix a row. It doesn't have to be a row, but generally you normally fix the rows, but you can also fix the column. This one you can play around with it and test your answers with the computer algebra system. So thank you for your participation. Let's see each other on Thursday. I'll communicate. My apologies. Thursday we had a very long day with meetings. I even forgot we had a class. But I was happy I could see something going on. So kindly continue with the discussions and I'll communicate in good time whether Thursday will be possible. If not, then we'll meet again on Saturday morning. Otherwise, thank you and I wish you all the best and bye-bye.